analysis, pollution, detection. It goes on and on. Pyroelectric body comp. And this is also more of the same in terms of many of these crystals here, PZT, strontium, titanate, bismuth, oxide, et cetera, et cetera. So, and these are some of the uses here as well. And you look at this other set here, electro-optical properties. Electro-optics, ferroelectric material, pyroelectric, and piezo. Innately, these candidates materials can be exploited one way or the other to serve you for sensors and detectors in the various range, okay? Importance of noise and fluctuation quantities. You might would think that the responsivity, and so to go through you just briefly, that you just need to get in your inventory of awareness about the electronic devices. Every system is going to have a responsivity, and that is implying the amount you get out for what you put in. And you would think that that would be the optimal quantity for characterizing the system. It turns out that it's this one, the specific detectivity that we just spoke of. Because every electrical system that you work with it fabricates its own noise. It generates its own noise internally. And I say we need to turn that air up a little bit. It's after lunch, and you know what I'm saying. My voice. You know, back in the days when I was teaching, Dr. Sharma, I always kept something in my hand and I would throw it. What I call young people napping in my class. So, Patty, I'm going to throw this myself. So I'm watching you. Keeping my eyes on you. I like humor in my lectures too, Dr. Sharma. It tends to wake folk up.
Glass of water is good.
Oh, okay. That's some water too, maybe. But then I may mess up all the electronics. and then there won't be any noise coming out. But anyway, these are important characterizing features for your system. Noise and equivalent power I just spoke of. Figure of merit as well, and I'll come back a little more, because for every engineering job that you're going to do, you can purchase the item off the shelf, or you have to fabricate it, and go make it for us. But then there are so many different items that you're going to purchase off the shelf, and everybody's going to claim is the best. But then as you get down to the nuts and bolts of it, you can see what the figure of merit or the specific detectivity, and then you can get your hands around which is actually the better. And of course, gain, once again, output versus the amount of voltage, input voltage output. And the bandwidth has so many different meanings now, depending on the context of the words. That's the first thing I need to say. There's band pass. There are band pass filters. There are band stop filters. But you have an understanding that the optimal word is contiguous, right? The United States, 48 contiguous states. So a bandwidth is going to have those contiguous frequencies that are right next to each other. So you put that in your hand. Just keep that. That's what you're speaking of when you're speaking of bandwidth is a contiguous range of frequency. And pretty much the same information can be carried in any bandwidth, in any frequency range. Now there's other physics and electronics, and that makes one frequency range preferred over another for different applications. But in principle, that should be the case. And some more ideas about figure of merits and which one you choose, once again, depending on which application you're trying to explore. If you need a low impedance amplifier, you need this one to be able to serve you best, or high impedance amplifier itself. And then the various physical quantities that we think about that go into characterization of the particular device. Okay. And these are some of the systems, and here we, once again, this is the material that we made the thin film of right here, and these are all crystals here. TGS, lithium, tantalate, strontium, barium, neobate, lead, lanthanum, zirconium, and titanate. So PLCT, and this is PVDF. We'll talk about that more. This is the pyroelectric coefficient. This is the ratio of the real part of the dielectric constant to the dielectric constant in free space. You will find, in case you may not know yet, that many of the physical properties of the materials will be as a complex number, complex function or complex number with a real part and an imaginary part that each can be measured separately. That's generally true for any structure that, and for typically. Then you will, for isotropic materials, then you're going to have anisotropic materials. And many of these quantities that are single complex become complex matrices. Okay, because things now depend on the particular direction that you're talking about. So why, once again, would you have these tight, thin films and compared to a crystal like the workhorse TGS or lithium navate, as the case may be, large surface area, lightweight, high strength and flexibility, robust in the infrared region. And this has another cartoon that shows the kind of the way that the lithium tantalate powder is encapsulated in the this is in the solvent that we finally make the thin film from. Okay, this you will find that when nanoparticles are dispersed within the film, it enhances the exportation of the properties that we're speaking of. It makes whatever we wish to exploit larger. Why? We do not necessarily, we don't have all the answers yet, but the nanoparticles are finding ways of enhancing systems even before we can understand the mathematics and the modeling that go into why that is the case. These thin films, micron in thickness, We can prepare them. We make these films in Patty's lab downstairs, and we can allow them to anneal overnight. Then we can extract them from the dish that they are in, and then put them into an arrangement and characterize them in the system. So we have three different types of, we have films then that have the PVDF TFB. This is polyvinylidene difluoride trifluoroethylene, and with lithium tantalate, and same with lithium tantalate with silver nanoparticles, and we go through the process then of making the film, and we do this here again as well. And this is the recipe, the structure or the protocol for making the thin film. This is methyl ketone. Is a solvent, and you put this material in the solvent. You have a P mixture. You can then put the nanoparticles into the structure as well, and we do ultrasonic dispersion. There's another problem that we have is that, and you will recognize that is the case, nanoparticles tend to coalesce, and there is a need, as we have seen, and I've not done much of this lately, I need to get back to the lab, but there is a need to perhaps have some way of keeping the nanoparticles separate from each other. And if you can keep them separate, that should enhance the functionality of the material as well. So we go through this and we'll anneal it, and then we apply electrodes as we've done here. So this is the nano composite system, and then it's ready for testing. And this is the system in Patty's lab here. And this is where noise is generated. This electrical noise. But overall, this is an outstanding system. And this once again some additional information about the systems that we've done at different temperatures. I won't spend much time. This is an illustration. This is the real part of the dielectric constant, and as a function of temperature on the abscissa, on the ordinance, is the real part of the dielectric constant. And this is with the triangle is with PLT1 with the silver nanoparticles, and this is without this is PLT1, and this is PVT. And you see an enhancement of this constant here in the entire temperature range, which is now just Patty's system in the lab is meant to characterize the system so that you have some working knowledge of how it is expected to behave. This is now the imaginary part of the dielectric constant, the epsilon double prime, and that too is plotted here as a function of temperature. And we do the same with the piezoelectric coefficient, and we get this enhancement here. This is with the silver nanoparticles, and it will be wonderful to know what is the nature of the mechanism that's generating this tremendous variability here, and we get the same in this situation here with as well. Okay, so just some idea of the conclusion. I guess I'm finishing early. The materials are flexible. Once we prepare the films, they are fairly homogeneous. The nano